Yes, today we're talking about electromagnetic compatibility, a very much hated but so important topic in electric circuit design. Let's break down what electromagnetic compatibility entails to begin with. There's two main subcategories. One of them are, of course, emissions. There's radiated emissions, and that's usually the ones that we think about. That's electromagnetic energy emitted into free space from a device or its cables. So this is the stuff that influences your radio directly through the air, for instance. Then one thing that's not thought of very often, at least not among semi-professionals and hobbyists, is conducted emissions. You also conduct interference signals over the supply lines or data lines. If you've ever placed a USB 3.0 cable too close next to some wireless receiver, you might have noticed that effect. Now, of course, there's always gray zones in between. Conducted emissions may radiate off a cable and become radiated interference, so they're often intertwined tightly. Then the opposite is, of course, also there. That's immunity or electromagnetic susceptibility, EMS. There's, of course, also radiated. A great example is when you had your old GSM cell phone too close to the car's radio. You could hear those GSM pulses in your FM receiver. That's a great example of an radiated immunity issue. Then, of course, the reverse for the electromagnetic interference over wires would be the susceptibility through wires. There can be noise on your power supply lines that, of course, spreads to other systems. And if those systems aren't immune enough, this will, of course, also cause issues. The radiated stuff is tested, radiated immunity is tested in specially controlled environment, usually absorber chambers of some sort, like anechoic or semi-anechoic chambers. There's coils to couple magnetic fields. TEM cells would be an example for doing it in lab. For the conducted, there's coupling, decoupling networks, or the bulk current injection method, which basically uses a very beefy current probe. Here's a few common and popular EMC standards, and this is really just a few. There's hundreds of them. I'm probably giving an understatement with hundreds of them. The most common one is the CISPR 11 Industrial Scientific Medical Equipment emission standard. Then CISPR 22 doesn't exist anymore, but is often mentioned in the literature. It's been replaced by CISPR 32. Most of the devices that you're watching this webinar on are tested against CISPR 32, like your laptop, your desktop PC, and that sort of stuff. The part that we're going to look at closer today is CISPR 25. This is a standard to protect vehicle components from immunity and emissions problems, with the target being the onboard receivers. And we will see in a second how old those standard limits actually are. Like your CB radio and AM radio that nobody uses anymore is well protected and other things are not, but that's for later on. Now, if there isn't a precise or specific standard for your use case, there's a bunch of generic standards. A few of them are shown here. What I, of course, left out in the intro are transient events like electrostatic discharge, surge would be a thing. Then you have in the automotive industry, you have things like load dump. This is where your battery contacts are loose and your alternator dumps all its energy into the electrical system. Reverse polarity. Everyone that's ever used a reverse polarity diode has done some sort of electromagnetic compatibility work. Then there are some very special ones at the bottom that I'm just mentioning because they appear in literature. The MIL standard 461G is a US military EMC standard that hopefully none of you are using at home. You could, but it's really nasty and difficult. And DO 160G is EMC for aircraft equipment. Just mentioning them alongside because they are commonly used. So, hope you haven't fallen asleep yet by all the standards that exist. We are looking at CISPR 25 today. The scope of CISPR 25, the standard applies to electronic and electrical components intended for use in vehicles, boats, and devices powered by internal combustion engines. So cars, motorcycles, things like that. Its purpose is also clear, and that is to provide protection for sensitive radio receivers against onboard radio frequency emissions. Here I have a standard line that's used for the standard limits for the voltage method. If you look at the frequencies, hang on, I got my laser pointer somewhere. Look down here, 150 kilohertz to what might that be, like 400 or 500 kilohertz. This is long wave radio. Then here there is Mittelwelle, what we call it in German, AM radio, very classic, up to 1.8 megahertz. In between, there is no standard limit defined. You could do whatever you want there, at least for this standard. Then here is 6 point something megahertz. This is, I think, 49 meter AM shortwave band. Nobody's using that either. At least, I don't know. If somebody is using that in their vehicles, please tell me in the comments. Here we're protecting the CB radios, and here we have VHF low band to here where the limit gets a little bit stricter is the AM radio, FM radio band. And yeah, that's the only things that CISPA 25 is protecting, at least for the voltage method. And yes, this does mean, maybe I should mention what's red and what's blue. The blue ones are peak limits and the red ones are average limits. And you have to stay below both of them for an average. There's a peak detector and an average detector, and both test results at each point have to be below the line. If you blow through one of them, your product failed. But yes, you can do whatever you want in between for this standard. And just looking at the protected bands, it shows how old some of these standards are, even though this is a new revision. So how can you do this at home? That's really the interesting question, or in your home lab, and how can you do this without blowing the bank? Electromagnetic compatibility is very expensive, which is good for people working in it because there's lots of money to be made with consulting and electromagnetic compatibility. However, it's really a budget problem for people that have to comply. Depending on where you're from, you may not even have an option to not comply. In the United States, there's FCC rules that force any product to be compliant. In Germany, we have the EMV-Gesetz, and on the European level, there's also a requirement that's, of course, ratified in national laws. Am I going to say something about this? Yeah, so this is a test setup. I'm just going to go over it real quick. We're going to go in more detail down the slides. So here I have a power supply. It's just a regular switch mode power supply. Goes into a power filter. From there, it goes into two LISNs, line impedance stabilization networks. What they are and what they do, we'll talk about later. Here, there's cable on some styrofoam. Here is the device under test, which in EMC is usually called equipment under test. Here is a passive load. Some people prefer to use resistors and solder them directly on there, but here I'm using the luxury of a passive load. All of that is mounted on a metal plate. It's galvanized steel, and there's also standard requirements for the size and material we'll get into later. One of the LISNs is connected to the spectrum analyzer through a transient limiter. Transient limiter is very important because setups like this are an easy way of blowing up the front end of your spectrum analyzer. Let's start with the reference ground plane. The minimum size for this method, and I'm only showing the voltage method in this webinar because it's by far the easiest method. And the other method, the current method, essentially builds on top of that. So you still need to do the voltage method setup to use the current method, except that things get a little bit larger. But for the voltage method, the minimum requirement for that ground plane is a size of 100 centimeters by 40 centimeters. So that is something that easily fits on top of a workbench. The reference ground plane's material and thickness is also determined by the standard. It must be made of copper, brass, bronze, or galvanized steel and have a minimum thickness of 0.5 millimeters. I think I put it in there again. Yes. In my case, it's exactly 100 by 40 centimeters, and the material is galvanized steel. The power supply also has special requirements, and as you've seen, I got away with just a normal a inexpensive laboratory power supply. But during the measurement, the DC voltage must be at its nominal value plus minus 10%. And what that nominal value is also, or is supposed to be, is also in the standard. For 12-volt supply voltage devices, which you find in common cars, is 13 volts plus minus 1 volt. For 24-volt systems, like large trucks, it's 26 volts plus minus 2 volts. You're allowed to use anything within those margins. One thing I'd recommend is that usually the higher voltage will yield the higher emissions. So if you want to make sure that you're below the limits, then use the worst case that you can possibly create. And now comes the challenging part. The power supply must be adequately filtered so that the RF interference generated by the power supply is at least 6 dB below the limits. And that's a problem because CISPA 25 limits are very strict, and most lab power supplies do simply not comply with that. An old linear power supply might actually be your friend, or in the alternative, you can use a battery. It's absolutely permissible to use a small battery. Do I have one here? Yes. Like one of these small lead acid batteries is always, even if you do HF, radio frequency stuff, batteries are always nice as a low noise source. Since I didn't want to do that, I did this. I used a regular lab power supply. It's a PeakTech 6227, which is in no way designed for inferior noise performance. Up here, for some common mode suppression, I have a simple ferrite. Just wind the power supplies through there 2 times. And then on the board, I have a line filter from Wirt. You can buy them, have the ground wires in there, positive and negative supply lines. The filter is bonded to the reference ground plane, and then my power supply leads move onto the listens. I don't have a measurement for that. I think that comes later. Yes, so whether or not this actually meets the threshold of the 6 dB below the limits, we'll see later on. Now the listen that I've mentioned multiple times, it must have a nominal inductance of 5 microhenries. It must be mounted directly on the reference ground plane, and the housings of the artificial network, maybe I should add here, the standard calls it an artificial network. Listen is the more common term. It's the same thing. When you read AN or listen or artificial network, it's the same thing. The standard says artificial network. It must be electrically bonded to the reference ground plane, and the return of the power supply must be connected to the reference ground plane. The measurement port of the artificial network, which is not connected to the measurement device, must be terminated with the 50 ohm load. Okay, we can do that. I should mention that, hang on, do I have another picture? No. Okay, we'll get back to that. But in my picture, there's 2 listens. There is an option with just 1 listen if the power supply leads are shorter than 200 millimeters or 20 centimeters. I prefer this setup with 2 listens for reasons we'll see later, regardless of how long the power lines are. Here's the inside of a listen. This is a TechBox TBOH01, which is the 2 listens that I'm using. It's a little bit fancier than just an inductor and some secondary circuitry. It has various protection devices built in. And yeah, it makes sure that the frequency response is the way it's supposed to be, which is the most important thing. It's called line impedance stabilization network for a reason. It's supposed to provide a stabilized impedance. The reason being, as you can imagine, every power supply, every car battery, the power supply system in different cars, they all have a different impedance. And for a standard, we need a standard environment with always similar, close to perfectly the same conditions. And this is one of the jobs of the LISN. Here we see the impedance profile, and here in green, that's the impedance profile of the LISN, the TBOH01. And then we have the CISPA 25 limits of permissible range here in purple. The other thing are CISPA 16 limits, which are not important for our setup. Here's the entire setup again. That is a drawing from the manufacturer of those LISNs. We have our two LISNs. And from the requirements that we read earlier, we're bonding the return line, so the ground line, directly to the reference ground plane. And the reason why I included this picture is these LISNs have external capacitors that you need to put on the LISNs. The reason being, some LISNs have those implemented, but then you cannot use that for, you can abuse one of those LISNs for conducted immunity testing, that's one thing. And you can even use these CISPA 25 LISNs for other standards, for instance, that DO 160 aviation standard if you wanted to. But those need to be added also. And we'll talk about the other details in the later slides. So here's a close-up of that setup. Here's the power supply lines that we've seen beforehand. Here's the large capacitor in the middle. Here's the small one. And from this perspective, you can see it better. You see that the ground sides of each LISN are bonded with copper tape to the reference ground plane. And you might be surprised, well, there's a red connector, positive. Here's a red one, and I'm putting a negative on it. Yes, that is actually correct. We're using each LISN for one of those lines. We're measuring what comes on the return line. Here it's better seen what comes on there. So we're using the positive side of the LISN, so to speak. So if we connect our spectrum analyzer to this port, we measure all noise and disturbances on the positive supply line, or coming back from the equipment under test on the positive supply line. And down here, if we connect there, it's currently 50 ohm terminated as per the standard, we would measure the noise on the negative return line. Separating those two has some advantages that I'll show later. Now, the one thing that we, of course, cannot meet on our benchtop setup is the requirement that measurements must be conducted in an anechoic chamber or in a shielded room. Not gonna happen. The standard demands it, but you're not an accredited test lab anyway. Anything you do is either pre-compliance, meaning you're trying to make your product as compliant as possible so that it hopefully passes compliance testing in an accredited lab. So in that realm, you can deviate as much as you want. However, you shouldn't, because you want to be as standard compliant, of course. Or what you're going to do is possibly diagnostic EMI, what I like to call it, is that some device causes some sort of interference, and you just want to measure what's going on. The ground plane is, however, grounded, and I will talk about those ground links later on also. A device under test must be placed on a support made of non-conductive material with a low relative permeability, epsilon R of less than 1.4, at a height of 5 centimeters plus minus 5 millimeters. That is the case. I'm just using simple styrofoam. Be careful. I've seen people use ESD foam, because ESD protection foam, because obviously bringing styrofoam into the equation might actually cause electrostatic discharge issues. But ESD foam is partly conductive. You cannot use it for the standard. The supply lines must be arranged in a straight line. This really should be highlighted, because you often see people laying long lines down in some sort of meander pattern. That's not okay as per the standard. And it's the same support, so same permittivity issues or requirements apply. And all sides of the device under test must be at least 10 centimeters away from the edges of the reference ground plane. I thought I had another picture of that. Yeah, I do, there. So we see, this is just my background measurement that I'm gonna explain in a second, but everything is away at least 10 centimeters from the edges, except the power filter and the load, but that is okay. What I'm doing here, I do not have a device under test. I'm just connecting the Lisen's power output directly to the load, run the cables over this styrofoam, and all I'm gonna do here is measure a background. Just to see the, for once we've read that the power supply noise has to be 6 dB below the permissible limits. That's one requirement. And the other one, if you were to use a shielded chamber, the measurement results from external interference are also supposed to be 6 dB below the limits. So to test both in one go, I'm simply measuring basically an empty board without an EUT. We can see here there's some long wires for current measurement going from the electronic load into this bench multimeter, is showing about 1 amp of current. Over here we also see about 1 amp of current, so that fits. And we're gonna see what we get. Oh, I got some close-up pictures. Nice. So here's the self-powered active load. It's a really nice alternative to fixed resistors, because this thing is extremely passive. It's not only extremely passive, it's also extremely quiet. So it's not gonna mess up your test results, and you can adjust all kinds of parameters. It has a constant current mode, it has a constant resistance mode, so it's perfect to simulating real resistors. It also has an external voltage control input, so you can actually vary those parameters if you would, for instance, be in a shielded enclosure or in a shielded tent. This may be something I should mention. There are tents that have about the size that you need, where you can put your reference ground plane in, and then you can still put it on your bench without having to buy a huge shielded chamber. Anyway, over here, 1 amp of current measured through those leads that go through this current measurement port. And the result is horrible. The gray stuff up here are the 6 dB margin. I know it's not visible very well, but you can tell that over here, there's some tiny dots that are over the 6 dB that we're supposed to be below the limit. So my setup, apparently, that way is not compliant for any testing. Well, it kind of sucks, because we wanted to see some test results, right? Well, remember those long leads that I had previously for current measurement? Actually, let me go back. That long stuff over here. Of course, this is a perfect antenna for all kinds of interference. And if we look at the frequency range, we can see that this is the FM broadcast band. So even that's not perfect, but just for fun and for comparison, I simply connected the two ports directly to each other, and look at the difference. This was measured beforehand, and this was measured afterwards. This is a very important lesson. I've been doing EMC measurements probably since I was 19, 20. And even I do stupid stuff where I simply leave wires in because I'm, well, let's face it, lazy in that moment and just want to check something real quick. Look at this huge difference. This is the same scaling. That's I think over here I even applied stricter limits. CISPA 25 has different limit classes. This is class 1 and this is class 3. And all of a sudden, everything is well below 6 dBs of the stricter limit. And here's a close-up. This is those are class 3 limits, and the gray stuff down here, that is the 6 dB margin. So again, up here, peak limits, average limits, and this is the actual measurements. This looks really nice. So let's measure something. This beast, many of you have seen before. There's a question that I'm gonna steer to. Gordon asks, should the power leads be twisted? You can, like really, this is your choice. if the wires will be twisted later on in their final application, then yes. When we talk about deviating from the standard test setup, you can do anything that will happen later on in the vehicle installation. Whether or not this will make a difference in this particular case is highly questionable, because there's almost no common mode noise. I'll spoiler that much. But yes, it can make a difference, and you are allowed to do it. As a matter of fact, you must do it if the device dictates it in its manual. The same thing, we haven't shown the case. The device under test is supposed to be 5 centimeters above the reference ground plane. So there's some devices, like let's take what are those things called that control the motor, ECU, I guess in English. They are often bonded directly to the chassis. If your device is directly bonded to the chassis with its metal casing or whatever, then yes, you will deviate from that in the test setup, and you will also bond it directly to the reference ground plane. So oftentimes the answer is dictated by how you intend your product to be used. Back to this beast. This is a buck converter. You find it on Amazon, and I see it in hundreds, if not thousands, of DIY projects. It says it has an LM2596S on there, but you should be aware, if you buy this thing on Amazon or similar places and you get $3, $4, $5 or something like that, it's a very cheap China clone. So let's not blame the original switch mode regulator for what we will see in a second. So here's the test setup. A lot more proper. By the way, you see I have a grounding connection here. The standard says you must have grounding straps every 30 centimeters, or in some use cases even closer. I'm intentionally not doing that because the standard demands that you bond every 30 centimeters to your shielded enclosure. I don't have a shielded enclosure, so I'm just using a regular ground wire, and even the diameter is technically not permissible because there's a requirement of a width to height ratio of 7:1. So this thin inductor could possibly maybe be this long, and that's it. But it's okay for the setup. Anyway, the two listens remained the same. Here I have my power supply wires. Here's the LM2596 buck converter. And here is my electronic load. The electronic load is set so that it draws about 1 amp. The output voltage is 5 volts. The input voltage is 13 volts as per the standard. And now I bridge this properly with some copper wire in between the terminals so that there's no external interference coupling in. Let me actually take a look at the clock. Yeah, it looks good. And that's the result. Horrible. And I'm just drawing 1 amp. That thing is allegedly rated for 2 amps, although some people have reported that it really gets hot. And the reason why I picked this device is because I know plenty of cases where people use these and have issues with all kinds of electronics. The funniest comment on my YouTube channel was a guy that used it inside a cat feeder to replace the batteries, and the cat feeder's RFID tag refused to work afterwards, so it wouldn't recognize the cats anymore, which makes sense because animal RFIDs are somewhere in this frequency range where the highest peak is. Let's talk about this for a second. So we see we have different colors here. The purple ones are the peak measurements. The green ones are the average values. And up here we have the limits. We see right here at around 160 megahertz, 160 kilohertz. We are way above the limit lines. I think in the peak diagram it was 32 dB above this one here, above the average one, 10, 20, 30, yeah, 32 dB. This is a lot. This is not a little. Due to this logarithmic display of voltage, this is in dB microvolts, it sometimes appears like it's just a little, but don't forget that 10 dB is 10 times the power, and 20 dB is 10 times the voltage, or 100 times the power. That's really a lot. Over here it's okay in the high frequency range, and we also notice something very interesting that's typical for switch modes. If you draw an imaginary line from up here through here, you can see that it's actually indeed a line. You would be able to fit a line. And here you'd be able to can draw straight like so. There's also an imaginary, there's another line that you could draw. This line up here has about 20 decibels per decade of attenuation, and down here we should be at around 40 dB per decade. This corner point right here has a reason why it's there. That is 1/pi of the rise time of the switching signal itself. That's very interesting to know. So the faster a switch mode regulator switches, the longer the decay will be, just 20 decibels per decade. In one of the what's it called? EEI? Electrical Engineering Insights, I said that efficiency is oftentimes the enemy of electromagnetic compatibility, and vice versa. Electromagnetic compatibility is the enemy of efficiency. If we switch extremely fast, we get rid of switching losses or minimize them, but our spectrum will stay higher for much longer, and that is a problem. And since we see that here, I just thought I'd point that out. Another thing I'd like to point out, you notice that here at the 30 megahertz mark, all of a sudden this all jumps up. This is not because the noise level really jumps up. It's the things that we haven't talked about, won't talk about. The resolution bandwidth up to 30 megahertz is 9 kilohertz. And here at 30 megahertz, it jumps to 120 kilohertz. More bandwidth, more noise. So this jump is simply just due to the measurement setup and not because of real inherent noise increases. Anyway, we're way above the limits, and now we need to fix it. So the first thing that I always read in my comments, really no exception, is either going to be capacitors or ferrites. Now, there is a funny graphic that correlates the amount of ferrites used to the skills of the design engineer. The more ferrites you see, the less skilled the design engineer is. Ferrites are oftentimes a last-ditch effort to gain a few dB of freedom when some product has failed. Never at any point should ferrites be your primary EMC solution. But since I know I'm going to get that comment anyway, try a ferrite, I thought, well, let's try a ferrite. And here's the measurement with the ferrite. You can see that there's now two traces. You see it here where there's actually differences. There's a bright purple, bright green, and a darker purple and a darker green. The darker one is the old without the ferrite, and the lower one is the darker one is the old measurement, and the brighter one is the current measure. So you see there's almost no difference, almost nothing except up here. And yeah, that didn't help us at all. Right, okay, I was just stunned for a second what I wanted to show. Now, let me show you the advantage. And yes, we'll get to solve this problem, but first we're going to look at something different. I mentioned earlier that I prefer using two listens because it gives us some advantages. And the advantage is being able to separate the kind of noise we're dealing with. What I'm using here is a listen mate, which is also from the company TechBox that produces these listens. And both listens are now connected to the listen mate. And now I have two outputs, differential mode and common mode. I hope everyone's familiar with common mode and differential mode, but a very brief recap is signals, the way we usually know them and learn them in school and university, travel in opposite directions. Like here, you'd have the positive supply going that way and coming back that way. At least from the technical standpoint, I know electrons flow that way and come back that way. Common mode would be both signals, like noise coming from over here, traveling on both lines, same direction, same phase, same amplitude. And so this is separating common mode and differential mode, so we can measure them independently. Yes, here's the drawing. The ListenMate is the newer version. I'm not using it, but the graph is the same. 2 listens, ListenMate, spectrum analyzer, and you can switch between differential mode and common mode. And here I have the differential mode. So that part of the noise that is traveling in opposite directions on the line. And over here, I have the common mode. So the amount of noise that's traveling in the same direction on the wires. You see over here these small peaks on the common mode. And if you remember the picture from beforehand, the only place where we had a difference here with the ferrite was exactly those locations. This is because ferrites suppress common mode, but that's not our main problem. Our main problem is differential mode, which is a shame because I wanted to show some sort of fancy filter, but we're not going to get a fancy filter, I'm afraid. So, the KISS principle. Keep it simple, stupid. 2 inductors. They are 470 microhenry inductors. And just out of, for simplicity, I put them right in front of the listens. Of course, I could have hooked them up at the input terminals of the equipment on the test. And that's, of course, where you would place them if you were to redesign an equipment under test. But just for this purpose, I put them right here. Remeasuring, these are still CISPA 25 class 3 limits. And look at that. That's all we need. Like I said, it's a shame because I was kind of hopeful that I needed higher order filters, but I don't. That's it. Problem solved. Now we can go for compliance testing. Now, in all honesty, here's a great example of something that would technically be above the limit, but is outside of the defined frequency range. If this was a real product that I would send off for certification, this would drive me nuts. Same over here. It comes awfully close. I would not be happy with that. I would still apply some more filtering. Also here, look at how close the average is coming to the average limit. But it would be, according to our setup, compliant. In reality, what you do out of it or do with it is another thing. Now, another thing I'd like for you to note is look at the remaining signal, particularly those shapes here, this little shape. If we go back to our common mode, look at that. It's exactly that shape. Because the inductors are only helping us with differential mode, but that's exactly what we had the problem with. So this actually works. If we'd add the ferrite on top of that, I didn't do that, then this would probably also go down a little bit. Here is just so that we can compare more direct. The dark ones are the old measurements without any filtering whatsoever. And down here, then the lighter colors, that is the new test result. I think that looks quite impressive. And most importantly, it's standard compliant. Yeah, that was it. Almost right on the mark, Brian, for 15 minutes for questions.
Well done. That was very interesting. That's the type of high-end lab stuff I don't do at home. But are you using this in production yourself, Sebastian?
Yes, all the time. Like I said, in Germany, we have this requirement, das EMV-Gesetz, which requires every product, anything that you sell commercially, even if you sell a kit to somebody, well, if it's assembled, if it's actually a kit they assemble, then you don't have to. But yes, I do use it a lot.
Yeah, and as you said, it's good money to be made in it because it's not cheap. But I'm glad you found some cheaper ways of doing the things. But I recall in 1979, Texas Instruments wanted to get their first home computer out, and they were going to plug it into TVs. But for that, they needed an RF modulator. And of course, the FCC wouldn't come to the party on approving the modulator. So now they had to ship it with a monitor and charge $1,150 for it. And that was in 1979 money, so that was ridiculous. And even after FCC compliance, I mean, the board, it had a ferrite bead on the AC power input, low voltage AC. And the entire motherboard was shielded in stainless steel. And still, you could hear that computer clearly thinking on your AM radio. And you could even hear it when you were typing because of shielding like that. Now, I see you starting off at about 150 megahertz. Do you also take into consideration things like plain old 50 hertz interference when designing products?
Yes, but that's a completely different topic. CISPA 25 goes from 150 kilohertz to 108 megahertz, at least with the voltage method. And this is an important point that you bring up, because all these standards have limits in certain ranges, and we oftentimes forget what's happening outside of it. I wish I would have recorded it, but this switcher, for instance, has a switching frequency of 50 kilohertz. We don't even see how horrible it is there, because we technically don't care. But on the 50 hertz, there's, for once, there's harmonics that happen, which are very important to take into consideration. And also, just as important is, your mains power isn't as clean as you might hope. If you would plug some sort of measurement converter into your wall outlet, you would probably need therapy afterwards. It's horrible what kind of nasty stuff comes out of there. So yes, you need to take that into consideration. That's why you usually have two pairs of filters. You have that power line filter that makes sure what comes in is clean. And then you have another filter that filters that nothing nasty goes out.
Cool. I have another question, but I think I want to get to the giveaway because people are used to that about this time in the show. I've got to remove your screen, put up my screen. Yeah, our webinar giveaway, there you have it, electormagazine.com/elector-webinar-giveaway. And the code word for today, I'll keep it nice and simple, EMC. Now, sometimes I see an EMC and I think compatibility. Other times I think compliance. What's the difference between being compatible and being compliant? Like you say, you've got bureaucratic institutions watching that stuff in Germany as well.
I'm just using those terms interchangeably.
Okay. Let's see, any audience questions here? Please bring them up. We want
I've
to see
seen a
more.
few.
Frank de Hart made it at last. Frank, you're late. I saw one from Gordon on the power leads being twisted, and another one from Gordon. What would be an estimate for setting up bench testing?
It depends on whether or not you already have a spectrum analyzer. Luckily, most spectrum analyzers that you even find in the hobbyist realm, like the Rigel one I have behind me, although that RSA is one of the more expensive ones, or if you have a Siglent SVA, for instance, or SSA, if you already have one of those, you'll easily get by with just $1,000. If you don't have one of those, of course, that part you'll also have to purchase that'll easily add 1,000 or 2,000. But what you see in the picture right there, you can get away with 1,000 easy, I'm gonna say.
Nice. And yeah, you did mention your power outlet being very dirty, even though it's slightly off topic for 50 hertz. I must add that I recorded a voiceover a few weeks ago, plugged my analog microphone into the laptop, recorded, thought everything would be great. No, there was a 50 hertz buzz. I should have unplugged the power supply when running the laptop with analog audio. Now, what you've got on the screen there, the setup looks pretty minimal, although impressive. It's 2 listens, a ground plane, and a buck converter. So for those who haven't done CISPA 25 testing, what's the most critical part of this setup?
The listen, clearly the listen. Everything else you can get by with very cheaply. For instance, the line filter I have there, I only need because I'm not using a battery. So if you have some lead acid battery sitting around, you don't need to filter. The equipment under test, which is the buck converter here, doesn't need to be hooked up to a electronic load. You can just use some resistors of some sort. So solder 5 watt, I don't know, 5 ohm resistor to your output terminals, and you're fine. So the one key thing is the listens, most definitely. And the same with the ground plane. I mean, yes, the standard says what kind of ground plane it has to be. If you have a piece of copper laying around that's smaller than that, use it. It's better than nothing.
Yeah, got another couple of comments and questions from George. He says, actually a simple setup with a Siglent spectrum analyzer can be put together for $3,000 if shopping wisely. And then,
yes, that includes the SA itself, correct? Yes.
and then Celso wants to know if we can use software-defined radios as a poor boy spectrum analyzer.
You can, but it's difficult. I intentionally left out having the way you have to set up your spectrum analyzers. The problem is you need the way the detection of peak, average, or quasi-peak, which I didn't mention because I didn't want to make it too difficult, but that's also one of the CISPR detectors. Setting that up and the way the spectrum analyzer sweeps the spectrum is very difficult with SDRs. One thing, well, let's talk about the specialized detectors first. So there's very specialized resolution bandwidths that are commonly not found inside hobbyist or amateur equipment, at least not of the lower kind. Even the Sigland SSA and things like that, you need a special option to have them. Like below 30 megahertz, you need 9 kilohertz of resolution bandwidth, and there's 120 kilohertz of resolution bandwidth above 30 megahertz, and then there's some other higher limit. That's oftentimes not possible. Now, with an SDR, of course, you can use GNU radio and build whatever you want to. The next thing is a traditional spectrum analyzer actually does sweep through the spectrum continuously. A CISPR-compliant receiver would step through the frequency band with a distance of half the resolution bandwidth. This is also something that's difficult to set up with cheap equipment. So yes, you can use an SDR, but you need to really watch a lot of small, intricate details, which can be found on the internet. But you're going to have to implement them on your own.
And you mentioned GSM phones back in the 90s. I mean, I don't know who got away with sending out GSM equipment over there that would go tick, 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 tick on your radio when your neighbor's phone was about to ring. That seemed a bit sloppy. Has the requirements become more onerous over the last, say, 20 years in getting your stuff certified or compliant?
Well, that is a very interesting case where everything is compliant, but it still annoys people. That's the funny thing. Just because something is standard compliant doesn't mean it's not going to cause any issues. I doubt that the very old FM radios really meet immunity requirements, but even a modern radio next to a GSM cell phone would give you those sounds. So the cell phone is meeting all its requirements, and the radio is also meeting all immunity requirements, and still you have some sort of interference. This is a really important thing to remember. The standards only dictate certain things in standard conditions, and life happens outside of those boundaries. Like, for instance, here we use those listens to have a very strict controlled impedance. Real world doesn't work that way. The same with your wall outlets. There are listens that, you know what? I love to get up and just grab stuff. There are listens that emulate your wall outlet, like this huge thing.
It's make that full screen.
Yes, so nice. That is a listen that simulates the standardized line impedance for wall outlets. Obviously, this thing is a lot bigger and heavier because it can handle 16 amps. Something might pass in that test setup with a listen like that and wreak havoc here in my wall outlet, because that wall outlet does not conform to standards. There is an ideal low impedance, but reality, I think I've seen a study from the United States up to over 100 ohms of line impedance for a wall outlet. It happens. So yeah, that's always the difficult part, deviating out of the test environment into the real world. Same with cell phone chargers. They might be compliant, even the ones from China. Put a 3-meter charging cable on there, you got a perfect antenna, and you altered the criteria.
Well, that's very enlightening for you to put it that way. So I'm just glad they moved up to 3G, 4G, and HSDPA, away from that GSM noise. Abdelali wants to know the code word. It's EMC, Electromagnetic Compliance or Compatibility. Sebastian uses them interchangeably. Guy wants to know what the downside of using a dual DC listen is.
Will my payment depend on the answer? No, just kidding. It's actually a very nice design. The cool thing is it's a dual listen, so you have everything in one case. You don't need to mount two different listens. The problem for CISPA 25 would be it's a 50 microhenry listen. It's good for CISPA 32 measurements, but not for the automotive range. So always depends what you want to measure. The listen is a very solid design. It looks nice. I wish they would have included the option directly in the device that you can separate common mode from differential mode, but that can be done even just with the math function of an oscilloscope. If you add the two outputs, then you get your differential mode. If you offset one, if you subtract one from the other, you get your common mode. So it's a very solid design. I wish I would have one, but I don't.
Well, I see you've got a buck converter there, and question from Instagram: would this be applicable to a buck boost converter?
Yes, this is applicable to any switch mode, to any non-switching device. The test setup does not depend on the equipment under test. The buck boost has, of course, the specialty that you can't just pick a point, say 12 volts in, 5 volts out, and that's all I'm going to test it. You have the buck mode and you have the boost mode. So you need to kind of check both of them. So you have to define some criteria under which you're going to test them. In professional test setups, this is determined in a test plan. Obviously, you're not just going to give your equipment to an accredited lab and say, here, test this for me. You have to define under what conditions. So just keep that in mind. If you test buck boost converters, you're going to have to check both cases.
Okay, and since you're somewhat of an expert on SDRs, I want to return to that topic. George said you could try the Great Scott or maybe Red Pitaya, but there are some cheaper options out there. Red Pitaya wasn't cheap last time I checked, so good point. And then, are you familiar with the Tiny SA?
Yes, I'm familiar with the Tiny SA. Same problem that I mentioned beforehand. Now, I always say wrong testing is always better than no testing. So yes, you can use those devices, but you will not be able to set the required resolution bandwidth and that segmentation of the steps. You will not be able to do that. You might be able to get the right step width by looking at how many points the device measures and how much span you set the device to, but then you're going to have to segment the spectrum into very small portions and somehow combine them later. And it doesn't have CISPA detectors. The average peak and quasi-peak are not implemented as per CISPA standards. But that said, if you have nothing else, then use it. And even use one of those old RTL SDRs. If you have nothing else, then use it by all means. I mean, odds are you're not trying to run an accredited test lab anyway. You're just trying to look at what's happening. And for that, sure, use it.
Great. And it's been a popular topic, Sebastian. I want to end off on a lighter note and go with a blooper. What have you been really puzzled by in the past that really surprised you that you had to solve an RF problem?
Honestly, I'd have to think about that. Surprised by an RF problem.
Yeah, I suppose you're too much of an expert now, so you'd have to go back 10 years or something to see you really flummoxed.
I guess the things that surprise me is air gaps that work. Like when a connector is broken off its PCB trace, but there's the space is apparently close enough that if you measure the device, you just notice, like, let's take a low noise amplifier at 10 gigahertz or above, and it just lost 20 dB of attenuation, of gain, and you can't figure out why. Everything looks nice until you figure out that one connector has actually broken off, but due to the close proximity, there's enough capacitive coupling that it appears to be on and appears to be working in general. You know, if it just broke up at lower frequencies, you just have a complete air gap and not measure anything. Those are things that surprise me all the time. It actually happens more often than you might think.
Oh yeah, I've had a few of them, and I don't have as much experience with you, so sometimes it's been a lot of head scratching. But
actually, no, I have another one. It was actually one of my recent shorts. That's what I want to talk about. I just recently found out, I mean, I've read it in literature before, but I've never paid much attention to it. We learn in school, which in school theory, I guess, is correct, that inductors do not have a polarity, which is electrically correct. But how much an inductor radiates actually depends on what way you solder it into the circuit. This has really amazed and stunned me, because I just tried it just for fun. Actually, the test PCB is still sitting behind me. All right, here, let's see if we can get that focused. The light is on. Yeah, we can kind of see it. There's two inductors on there, and the only difference between the two is their orientation, right? So if you apply the same signal to both of them, the spectrum is actually entirely different. The false direction radiates about 6 decibels more, and 6 decibels is, again, a lot. It's 4 times the power or 2 times the voltage. That really surprised me a lot, because I'll admit I've never paid attention to it, because I thought, well, those are esoteric effects. Who cares? But that has surprised me.